Welcome students, welcome to the next class of laws of motion, and today we are going to discuss a topic of laws of motion for the 10+1 students. And first of all, hope all of you are doing well. First of all, as we know, the topic name is laws of motion, but you have to go through some Newton laws basic statements as well to understand the topic. Today's topic is all about why Newton's second law is the real law, and we are also going to discuss the conservation of linear momentum. But before that, I have to give you some knowledge about Newton laws as you have done in 9th and 10th class, but I think some briefing of the knowledge is required for these kind of topics. So first of all, what is Newton's first law? Now Newton gives us three laws actually. Now what is first law? Now Newton's first law states that if anything is at rest, or if anything is in motion, or anything which is in a particular direction will remain in that state until an external force applied on it. Now obviously this law contains three aspects. The three aspects are rest, motion, and direction, which means if anything is at rest, it will remain at rest. If you are not going to touch your book, obviously physics book, then it's not going to change its position by itself, which means that is Newton's first law. I hope not many students are doing that Newton first law application with the physics book, okay? And now if anything is in motion, now you can take it as a particular motion or a uniform motion you can take it as. So if anything is in uniform motion, it will never reduces its speed, because if we are talking about Newton's first law, then it's not going to change its speed, which means it will always remain in uniform motion until an external force applied on it. On basic things, on practical grounds, the force of friction, the friction of air reduces the motion. So if we are going to neglect these external forces, the motion is always going to be uniform. So that is how we can understand that. Now direction. If anything is in a particular direction, it can never change its direction by itself, which means a particular external force is required which is going to change its direction, okay? That is how Newton's first law works out. To understand it properly, you can just take a practical example. You can take example of passengers moving in a bus, because that example can obviously explain these all three types of, you can say, Newton's first law, which means now this is not going to types, this is going to be how we can define Newton's law in three forms, okay? Now if the passengers are moving in a bus, okay, and if the bus suddenly starts, now if the bus suddenly starts, how it's going to impact the passengers? Because the bus suddenly starts, the lower part of passenger is now moving, but the upper part want to be in rest. So that's why we fall backward, okay? Whenever a bus suddenly starts, the passenger of bus suddenly falls backward, because the lower part move with the floor of the bus, but the upper part want to be at rest. So that is how we can give example of that in the rest segment, that is also known as inertia of rest. Now similarly, we can take example of motion in the same bus. If the bus driver suddenly applies brakes to the bus, now the bus is moving obviously, then if a bus driver suddenly applies brakes, now what happens to the passengers? The lower part suddenly comes at rest because the bus is now stopping, but the upper part of the passengers, okay, now it want to be in motion. That is why all the passengers fall forward. So that is how it's going to happen, okay? So which means we can easily have a impact of all the three inertias in the single example. If bus suddenly starts, the passengers fall backward, and if bus suddenly stops, the passengers falls forward. That is due to inertia of motion. Inertia of motion, that is also going to be the part of the Newton's first law. And similarly, if we are on a hill area and the bus suddenly takes a sharp turn, and if we are taking a sharp turn on the left hand side, the passenger is always going to fall on the right hand side, which is also due to centrifugal force. But if you are going to discuss Newton's first law and the inertia of direction, obviously if there is going to be a circular motion just like that, now the road is just like that and the bus is moving in a direction, you are always going to fall outside the circle, which means if the bus curves around left hand side, you are always going to be shifted toward the right hand side of the bus. That is, you can experience by yourself. Hope so you have the experience of that. That is how we can understand all the three parts of Newton's first law by a single example. Okay, now this law gives us the statement of force as well, because now force can be defined as any physical quantity which can change the state of rest or motion or a direction. Now that physical quantity is defined as force, and afterwards it can we can explain that force can be a pull or push which can change the state of the body. That is how the statement of force comes from Newton's first law. Now hope so you are now understanding it better, Newton's first law. Now I am moving to the Newton's second law. Now what is Newton's second law? To understand it better, you have to go through the momentum. Now, what is momentum? Actually, the momentum is the quantity of motion contained in any body, which means it is going to be proportional to the mass, and it is also going to be proportional to the velocity of the body which is moving. So which means in a simple words we can say that the momentum, the linear momentum, which is having a symbol of P, can be taken as mv, which means product of mass and velocity, which means the linear momentum is proportional to the mass of the body and it is also proportional to the velocity of the body, and product of that is known as linear momentum. Now if you are having the basic knowledge of linear momentum, you can also define the SI units of linear momentum, which is going to be very simple. For mass, that is kilogram. For velocity, that is going to be meter per second. And obviously you can also define dimensional formula from that. Now mass is having m, and obviously velocity is having lt minus 1, so that is going to be the dimensional formula of linear momentum. Now what is Newton's second law? Newton's second law is simply the rate of change of linear momentum, which is proportional to the external force, which means the external force is always going to be equal to rate of change of linear momentum, which means dp upon dt. Now that is going to be the Newton's second law. And obviously from that simplest of law you can also define the basic particular law. In a magnitude you can just take d upon dt of, now you can take the value of p, that is going to be mv. Now that is the vector form. Okay, so now in magnitude you can simply have that, so which means mass of body is always going to be constant. Now what is dv upon dt? The rate of change of velocity is known as acceleration, as we have done in the previous chapter. So which means that formula can be defined as f is equal to ma, that is also known as Newton's second law. But I advise you to remember that thing, because that thing is contained in the statement of Newton's second law. The rate of change of linear momentum is equal to the external force applied, which means F is going to be dp upon dt. Now you can also derive F is equal to ma from here. This is going to be very simple. Okay, now what are the examples of that? We can just take one or two examples of that. So to understand it better, obviously the students are always interested in practical examples. Now all of you have played cricket. Obviously you have catched the ball. Now why a cricket player lower his hand while catching a ball? Now, if we are, now I am talking about cricket ball, which is the leather ball, okay, so which is quite heavy and hard as well. So if you are going to lower your hand, then it is not going to hurt your hands. Now, that is why if we lower our hand while catching a ball, obviously we are always going to increase that time interval. And if the time interval is increasing, obviously the momentum is going to decrease. And similarly, the force that which is going to hurt your hands is also going to decrease. That is how this happens. That is why this Newton law is having this kind of example. Okay, that is how we can explain that. Now that is a very simple thing, dp upon dt, and this is going to be the Newton's second law, and we can explain like lot of examples through that formula. Now the vehicles are having shockers. All know, all the two-wheelers and four-wheelers are always having shockers. Now the shockers are going to increase the time interval of the shock. That is why the passengers feels comfortable over riding that car, or you can say the bike. Okay, so that is why that is not that force of jerk is not going to impact you. So again the same thing, they increase the time interval, which reduces the momentum and always reduces the force. That is how we can explain this. Now this is having a lot of examples. All the glasswares or chinawares are wrapped in the thermocol, okay, or they need packaging, because that packaging also increases the time interval and reduces the shock of the force. So there are a lot of examples of that. You can take so many examples by yourself as well. Now the Newton third law. Now we are moving to the Newton third law. That is also going to be very easy. Now what is Newton third law? It's the simplest of all. Every action is going to have a reaction, equal and opposite reaction, which means if any force is, we can take F12, which means force on 1 by the 2, then that is equal to minus F21, negative of 21, which means the force on the second body due to first. So that formula describes the Newton's third law. Every action is having a equal and opposite reaction. That is how we are going to explain that. Okay, now hope so. Now you have the brief knowledge of all the Newton laws. Now we can continue with our topic, that is going to be why Newton's second law is known as a real law. This law is known as a real law. So now we can explain that. Okay, so this is going to be very simple topic for you. Now if you are having the knowledge of all the laws, hope so. Now you having the knowledge of all the laws, why Newton's second law is called real law. Now how we can explain that? Newton's second law is known as a real law because the first law and third law can be derived from the Newton's second law. So we are now going to explain it. Now as you know, now Newton's second law is F is equal to ma. Now this is going to be a simple second law, as you know. Now in that law, if external force is 0, if external force is 0, which means F is going to be 0, therefore ma is going to be 0. And obviously mass can't be 0, as you know, mass of the body can't be 0. So therefore acceleration is going to be 0. Now what it means, if acceleration is 0, which means either the body is at rest or moving with uniform speed, which means that is going to have the Newton's first law. Now which means anything is going to be at rest forever if there is no external force, and obviously if that is in a motion, so which is always going to be moving with a uniform speed, because if there is no external force, the body is always going to move with the uniform speed. That is how we can explain Newton's first law from the second law. And now similarly, we can also explain Newton's third law from that. Now we are taking two bodies here, so one can be named as 1, that is can taken as 2. Now the downward force can be taken as F12 and the upward force can be taken as F21. Now according to Newton's laws, we can explain that. Now according to Newton's second law, now what is F12? That is the force on first body by the second, which means F12 can be taken as dP upon dt. Now you can take it as a 1 as well, okay? So that should be marked as equation 1. Now similarly, the force on the second body, taken as F21, which is taken as dP2 upon dt. That should be marked as question number 2. Now we have just applied Newton's second law to the two bodies which are in direct contact with each other, which means F12 is the force on the first body due to second, and similarly F21 means the force on the second body due to the first. Now these two forces can be added, so we can add equation 1 and 2. Now how it's going to impact? F12 is plus, yes, F21 is equal to, yes, dP1 upon dt plus dP2 upon dt. Now if there is no external force, so which means now that thing now going to be 0. If dP1 upon dt plus dP2 upon dt is going to be 0, therefore F12 plus F21 is equal to 0. Now this is going to solve our Newton's third law. Now what is Newton's third law? Newton's third law is very simple. So which means F12 is equal to minus F21, and which is the basic statement of Newton's third law. To every action there is an equal and opposite reaction. That is how we are going to solve that. So which also proves the Newton's third law is also contained in the second law. That is why the Newton's second law is called the real law, because it contains the first law and the third law. So also from that topic smartly, we can also calculate the conservation of linear momentum. Now how we can solve that from that topic is going to be very easy. I am just going to erase that part. Now if you want to solve another topic which is known as conservation of linear momentum. Now from that part only, as you have already explained, dP1 upon dt plus dP2 upon dt is 0. That is known as no external force, which means P1 plus P2 is equal to 0. And similarly for n momentums, if the momentum term is now taken as n, so which means for n terms we can just take for n terms, which means P1 plus P2 plus P3 and up to Pn, that is going to be 0 or can be taken as constant, which means the sum of all the momentum is always going to be constant, and this can be easily explained. Now how we can explain that? For an isolated system, the sum of the linear momentums is always going to be constant, and which is also taken as the conservation of linear momentum law. That is how you can also derive the conservation of linear momentum from Newton's laws as well. So that's going to be very simple. Always remember that the linear momentum is conserved for any isolated system. Now what is the meaning of that isolated system? Which means the external force is always going to be constant or zero. It is how we can explain Newton's laws and why Newton's second law is known as a real law, and also we can also explain from that the conservation of linear momentum. So that is all for today. Hope you all are doing well, and if you like that video, then like and subscribe our channel as well. Thank you so much.